Hello everyone. Thank you for attending our presentation for IEEE VR 2026. My name is Donghae Lim, representing Integrated Media Environment Laboratory at the University of Osaka. Today, I am excited to present our research titled CaliView, Continuous Viewpoint Calibration Using Dynamic Rotation Gain Control. Here is a brief outline of my presentation. I will start with the introduction and background of our research, move on to explain the proposed CaliView system, discuss our experimental evaluation, and finally wrap up with the conclusion. Let's begin by looking at the problem. Head tracking allows VR users to freely explore a 360-degree environment. However, there are many cases where the camera viewpoint needs to be adjusted. For example, when a user is seated, the physical rotation of their neck is heavily restricted. Alternatively, a user simply might want to change their viewpoint without changing their physical posture. Typically, camera rotation or viewpoint resetting is performed through manual input using controllers, such as the widely used snap turn. While this is effective, it could potentially undermine immersion. Furthermore, the constant need for additional manual manipulation can increase cognitive load and mental fatigue during the VR experience. To address spatial limitations, prior research has extensively explored redirected walking. Redirected walking subtly redirects users by applying gains to the amount of physical change, such as translation, rotation, curvature, and bending gains. However, because redirected walking primarily assumes that the user is physically walking, it is highly challenging to apply these techniques to stationary or seated VR experiences. Outside of redirected walking, researchers have used amplified head rotation, simply known as rotation gain. This applies a multiplier to the ratio between the virtual rotation and the real-world physical rotation. For instance, a small physical turn by the user translates into a much larger virtual turn. However, applying a constant rotation gain has a critical limitation. The user's forward-facing body orientation remains unchanged. When they look back to the center of their physical space, they will still be facing their original starting direction. This brings us to the purpose of our research. We propose CaliView, a novel method for continuous viewpoint calibration in immersive VR. CaliView introduces dynamic rotation gain control, adapting the calibration in real time without any explicit user intervention. Our goal is to enable robust and seamless calibration during natural user movement, reducing disruption to immersion. We believe CaliView holds great potential as a reorientation technique in VR applications that provide a target orientation, such as racing games or parkour games. To validate this, we evaluated its effectiveness through a between-subjects experiment with 75 participants. Now, let's dive into the core mechanics of how CaliView actually works. The main concept of CaliView is to dynamically adjust rotation gains to naturally calibrate the user's physical orientation to a target orientation. How is this achieved? The disparity between the user's present body orientation and the target orientation determines the rotation gains. For example, if the system wants to orient the user to the right, it will apply a higher gain when the user turns their head to the right and a lower gain when they turn to their left. As the user naturally looks around, this asymmetrical gain subtly shifts their physical center. This unknowingly guides the user to face forward perfectly aligned with the target orientation. Of course, for CaliView to work, the system needs to know the target orientation. How to determine this differs depending on the specific application. In our study, we used a navigated path toward an objective as the target orientation. Similar to the in-game navigation lines seen in games like Dead Space, a continuous visual line guides the user, serving as a reliable anchor for the system to calculate the necessary rotation gains. To ensure these gain adjustments remain imperceptible to the user, the upper and lower limits were carefully determined by referencing previous studies on detection thresholds and by conducting our own preliminary experiment. Assuming a maximum turn angle of 120 degrees, we set the upper limit to 1.83 and the lower limit to 0.69. Crucially, regarding the gain coefficients based on rotation velocity, we implemented a quadratic dependence. We specifically chose a quadratic function to avoid the sudden or jarring changes in gain that are often seen in linear or exponential models. This ensures a much smoother visual experience. Next, we will discuss how we evaluated our proposed method. To examine the effectiveness of CaliView, we conducted a between-subjects experiment comparing three conditions. First, CaliView only. Second, snap turn only, which represents the conventional baseline. And third, a hybrid condition, which combined both CaliView and snap turning simultaneously. We recruited 75 graduate and undergraduate students, assigning 25 participants to each condition. They used an HTC Vive Pro I HMD and navigated a virtual environment generated with the Unity engine. For the experimental task, participants were asked to collect 25 green tokens per session, with no time limit. As you can see on the right, the tokens appeared sequentially, and a green line indicated the shortest path. We intentionally designed a very simple item collection task. Our goal here was to clearly isolate and clarify the fundamental advantages and disadvantages of our proposed method, without the confounding variables that a complex virtual environment might introduce. The token order was strictly controlled to ensure identical travel distances and rotation demands across all conditions. We collected both objective and subjective data. For objective evaluation, we measured the total time taken, the number of snap turns used, the number of teleports used, and the accumulated rotation angles of both the physical HMD and the VR camera. For subjective evaluation, participants completed standardized questionnaires, including the System Usability Scale, the Simulator Sickness Questionnaire, the NASA TLX for perceived workload, the IPQ for presence, and a custom discomfort score. Let's look at the objective results. The most notable finding was that participants in the hybrid condition used 19% fewer snap turns compared to the snap turn baseline. This proves that CaliView effectively handled much of the reorientation implicitly, reducing the need for manual inputs. We also found that participants in the CaliView only condition rotated their physical heads significantly more than the others, simply because they relied entirely on head movements for calibration. Importantly, no significant differences were observed among the techniques regarding the number of teleports or the rotation of the VR camera. This indicates that the continuous adjustment of CaliView does not hinder or disrupt standard locomotion behavior. Moving to the subjective evaluation, we found no significant differences among the three methods in terms of perceived workload, usability, sense of presence, or general discomfort. However, we did find a significant difference in simulator sickness. The SSQ total score for CaliView was significantly higher than that for snap turn. This suggests that the increased physical head rotation required by CaliView may induce slightly higher levels of cybersickness. So, what do these findings mean? CaliView successfully enabled 360-degree virtual rotation without overt user interaction. However, the increased HMD rotation likely contributed to the higher SSQ scores. This highlights an interesting trade-off. Snap turn requires manual input, which can lead to mental fatigue and breaks in immersion. CaliView removes manual input, but can introduce physical fatigue. Therefore, the hybrid approach proved to be highly effective. It significantly reduced the need for manual snap turning while mitigating the physical fatigue associated with using CaliView alone. Integrating CaliView with existing techniques like snap turn appears to be the optimal solution. We acknowledge a few limitations in our current work. First, CaliView requires a predefined target orientation. Therefore, it is impractical when the destination is unknown. For example, in a maze exploration task, the continuously adjusting function could actually have a negative impact and disorient the user. Second, the study was conducted in a relatively simple environment, so further evaluation in more complex scenarios is needed. Finally, the rotation gain parameters were fixed for all users. Implementing a personalized calibration process could further improve usability and help reduce the motion sickness issues we observed. Finally, let's wrap up with our conclusion and future work. In conclusion, we proposed CaliView, an implicit reorientation technique using dynamic rotation gain to overcome limited physical turning constraints. Our evaluation demonstrated that CaliView achieves performance, usability, and workload comparable to the conventional snap turn. Furthermore, the hybrid approach successfully reduced user interaction without sacrificing overall performance or usability. For future work, we plan to focus on methods to determine target orientations in diverse scenarios. We also aim to apply CaliView without a predefined target orientation and validate long-term effects such as fatigue accumulation under more complex conditions. Thank you very much for your time and attention.